This is the quiz on periodicity and photoelectron spectroscopy. In question 1, we're looking for the highest second ionization energy, which means we'll lose one valence electron, but the second would be a core. I don't want to lose the core electrons because they're nice, full, stable orbitals. They have a full energy level in the second and first with something like a sodium +1 ion. So I don't want to lose the second electron. That would be a core. Question 2 are groups of elements, and we're looking for a trend in ionization energy. There's this equation that we'd mentioned earlier. It's called Coulomb's law. E equals Q1 times Q2 over R squared. In our case here, it's going to represent ionization energy as a function of two variables. Number 1 is the magnitude of the charge. Q1 and Q2 are the magnitude of the positive and negative charge. In an atom, that's going to be the number of protons and electrons. And then R is the radius, or the distance between the nucleus and the electron cloud. If you have a group like aluminum through chlorine going across an energy level, for the most part, R is the same. Aluminum through chlorine, they're all putting their electrons in the third energy level. But the magnitude of the charges increase as you add a proton and an electron. You have a greater nuclear charge. You could say greater Coulombic attractions. So chlorine with the most protons and electrons has the strongest attraction between the nucleus and the electron cloud. It would take the most energy to remove electrons from chlorine. The second two groups going down the alkaline earth metals and the halogens. As I'm going down a group, now the biggest factor is the R, the radius. I'm putting electrons in higher energy levels, which means the attraction is weaker between the nucleus and the electron cloud. So the attraction is strongest in the smaller atoms like fluorine. At the top of the group, where my electrons are really close to the nucleus, the attraction is strongest, and I'm going to need the most energy to remove electrons from small atoms like fluorine, or it should be beryllium. The last choice, you have to be careful when you have a series of ions. Check to see if they're isoelectric, meaning they simplify to the same number of electrons. So when I take the charge into consideration, all 4 of these ions have 10 electrons. So they have the same electron structure, they have the same R value, but magnesium ions have the most protons, which means greater nuclear charge, stronger attraction. So the magnesium +2 ion is going to have the highest ionization energy. So you have to be a little careful because this is not the trend if they were neutral atoms. If they were atoms, neutral atoms, we would expect sodium and magnesium in the third energy level to have the highest radius and the weaker attractions. But not as ions. They all have essentially the same radius. So now it goes to the greatest number of protons. Question 3 was fine. General trends in increasing radius and ionization energy. I could give question 3 to first-year kids, knowing that in the second energy level, fluorine and chlorine are smaller than sulfur, but not fluorine and chlorine, oxygen and fluorine are smaller than sulfur, but between oxygen and fluorine, fluorine has the smaller radius because it's got an extra proton, which then is the opposite trend in ionization energy. If I'm going increasing ionization energy, the smaller the radius, the greater the attraction, the higher the ionization energy. Question 4, they're all right, which makes you second guess yourself. Because if I compare neon to boron, I'm going across the second energy level, and there's more protons and more electrons. In neon, I have a greater effective nuclear charge. You could say greater Coulombic attractions, which makes the radius of neon smaller and the ionization energy of neon greater. In question 5, I think you sound like a broken record sometimes, in that everything revolves around this attraction between the nucleus and the electron cloud. So here's a fluorine ion with a smaller radius than an oxygen ion. Same number of electrons, they're isoelectric, but fluorine would have an extra proton. Question 6. is the general equation for electron affinity energy. It's the opposite of ionization energy. If you had to write an equation for ionization energy, we might write it maybe something like this. Ionization energy is energy you have to add to a neutral atom to remove an electron and form a +1 ion. And then we'd release the electron. Electron affinity energy is energy released when we gain the electron. If I gain an electron and form a negative ion, I'm filling the energy level, which then is forming something really stable, and energy is released. Electron affinity energy goes hand in hand with electronegativity. That if I have an element that has a higher electronegativity, it has a higher tendency of gaining electrons, it's more attracted to electrons, it becomes more stable by gaining electrons. It would typically form a negative ion. Well, now when they do gain that electron, they're going to release energy. So we normally don't really talk about electron affinity or even electronegativity in reference to like the group 1 alkali metals or alkaline earth metals, because why would they be gaining electrons? They become more stable by losing electrons and forming positive ions. So electron affinity is really for the negative ions. When I gain an electron, I would release energy. I like question 7. When you have a list of successive ionization energies, look for the big jump. Somewhere there's going to be a big increase, a significant increase in ionization energies. That's the switch from valence to core. We'll lose the valence electrons, but the core would represent the nice full orbitals, a nice full outer energy level. And it would take a lot of energy then to remove a core electron. So this element in question 7 must have 4 valence, so it would typically form a +4 ion, but we don't want to lose the 5th. Now, ionization energies will always increase because each time you lose an electron, the charge on the electron cloud decreases, but not the charge on the positive nucleus. There's always going to be more protons in the nucleus that would have a greater attraction for the electron cloud as you keep losing electrons. So they'll always increase. Ionization energies will always increase as you keep losing electrons, but not protons. But here we're looking for that significant increase, the switch from valence to core. Number 8, here's a graph of ionization energies. This graph will show us that there are 2 exceptions. I mean, normally we expect ionization energy to increase going across a group, but there's a little bit of a decrease from beryllium to boron when you go from the full s orbital to a p orbital with just 1 electron. It seems like it's actually more stable just to lose that p electron. Like in boron, for example, there's just 1 electron in the 2p orbital. But if I lose that, now I'm down to beryllium, and it's just got s orbitals, and they're nice and full. The other exception is going from nitrogen to oxygen, where there is another little dip in ionization energy. And now that's because nitrogen has a pretty stable configuration where you've got 3 electrons in the p orbitals, but everybody gets their own orbital and there's no repulsion. If I go to oxygen, I'm going to have to add another electron. And for oxygen, somebody's getting paired. And that just causes a little more electron repulsion. And so it's easier to remove that 4th electron. Question 9 gives us a photoelectron spectrum. This should be chlorine. The photoelectron spectrum gives evidence of the orbital model. It gives us evidence for trends in ionization energies. I like to label the peaks, and I always start with the peak that's at the highest ionization energy. That will always be your 1s orbital. The 1s orbital is right next to the positive nucleus, and it'll experience the greatest attraction. So the highest ionization energy then comes from your 1s. And then if you follow it out, it should follow the pattern of orbitals on the periodic table. the magnitude of the spectrum or the signal, the magnitude of the peaks, tells you the relative number of electrons in that orbital. So like peak Y goes up 5 units, and that peak in the middle would be your 2p6. If you add up all the electrons, then this should be chlorine. Question 10. Peak X and peak Y then correspond to the 1s orbital and the 3p orbital. Sometimes they might refer to them as subshells. Subshell would be the same as an orbital. Question 11. The electrons in orbital X of the element shown below have a binding energy of 273 megajoules per mole, while the electrons in the same orbital of sulfur have a binding energy of 239 megajoules per mole. What can we use to explain the difference? Okay, so we identified element X as chlorine, and chlorine has 17 protons. Sulfur would have 16 protons. So if we're looking at the same orbital, they're referring to the 1s orbital. And essentially we're saying then, why is there a stronger attraction for the 1s electrons in chlorine versus the 1s electrons in sulfur? And it's just that sulfur with one less proton has a lesser nuclear charge. And finally, question 12. Peak Y represents the electrons of the outermost orbital of the element shown below. If a student were studying the PES spectrum of bromine. Okay, so we know this one is chlorine, so now we're going to compare it to bromine and label the outermost orbital as peak Z. How would the intensity of Z and the binding energy of peak Z differ in an atom of bromine? These are really good questions. Okay, so the intensity represents like the height of the peak. That's just the number of electrons. But if we're comparing chlorine and bromine, they would both have 5 electrons in their outermost p orbital. So the intensity of the peak would be the same, but because for bromine it would be the 4p with 5 electrons, the electrons would be farther from the nucleus, and that energy binding the electron then to the nucleus would be smaller, or the ionization energy would be smaller.